I'm going to try to quickly explain the fundamental theorem of calculus, but to do so I have to start off with just a quick review of the derivative. Okay. So when you think of the derivative, you want to think of the slope. And it's the slope at any given point, instantaneous slope. So given the sine curve, if I take the slope, say at the origin, that slope is about a slope of 1. Okay, so if I say the slope when x equals 0 is about a slope of a 1. Okay, now let's say what's the slope at pi over 2. Okay, here's a 0 slope. Now let's find the slope at pi. Okay, here it looks like we have a negative slope, or a negative 1. And then my slope down here at 3 pi over 2 again is a 0. And my slope, if I was drawing exactly to scale, at 2 pi would again be a 1. Okay, and what I can do with these is I can transform these into grid coordinates. And if I plot each one of these grid coordinates, at x equals 0 I have a slope of 1. At pi over 2 I had a slope of 0. At pi I had a slope of negative 1. At 3 pi over 2 I had a slope of 0. And at 2 pi I had a slope of 1. Okay, now if you notice, if I add more points in here and I fit a curve to these dots, what I'm going to get is the cosine curve. Okay, therefore the derivative of the sine function is cosine. Okay, so I'm going to make the connection that the antiderivative, or the integral, is the area under the curve. Okay, easy way to remember is area under the curve. It's really the area between the curve and the x-axis. Okay, the way I can do this, similar to the slopes here, is I can add rectangles under the curve, and I have to figure out what is the area under the curve. So an easy way to do this is through estimations, in which case I'm going to put 8 rectangles under the curve. So my delta x, or the base of my rectangle, will be 2 pi minus 0, my upper limit minus my lower limit, divided by 8 subdivisions, or n equals 8, which is going to give me pi over 4 as the base of each rectangle. Okay, so here's my first pi over 4. Okay, and I'm going to use the midpoint method, in which case the middle point of this subdivision, okay, this represents my delta x. The middle of this subdivision is going to touch the curve here. And this becomes my first rectangle under the curve. And as you see, there's a slight overestimation here and a slight underestimation there, and it's all going to work out nicely for this purpose of this demonstration. Okay, so now I'll complete the drawing. My second rectangle goes from pi over 4 to 2 pi over 4, or pi over 2. And again, I'm using the midpoint method, so the middle point of my rectangle will touch the curve. Okay, again, here. Now I just want to quickly calculate the area of each rectangle. Okay, so the first rectangle is going to be that base times the height. And the height is the cosine function evaluated at that midpoint, which is pi over 8. Okay. And each rectangle after that will go in odd numbers, so the first will be pi over 8, then 3 pi over 8, and so on. The area of my first rectangle is a positive 0.726, which makes sense. This one is a larger rectangle. This one's slightly smaller, it gets a value of 0.3. 2 and 3 are exact opposites. 3 is below the x-axis, so it's going to be negative, and that's a negative 0.3. Okay, so now what we want to demonstrate is, we'll call this g of x is going to be the integral from some starting point, we're going to say 0, to some value x. And that's going to be for whatever my current function is. Okay, in this case our current function is cosine, but this is going to indicate, or going to represent, the area so far. Okay, so if I call this g of 0, that'll be the area from 0 to 0, given the cosine of x dx. Okay, and without integrating, we're just going to use the estimations. If I go from 0 to 0, I'm going to have 0 area. Becomes the integral from 0 to pi over 4. Okay, and what this is this saying the area under the curve from starting here and ending here, or the area under the curve from here to here, which is the area of my first rectangle. If I continue and I say g of pi over 2, it becomes the area under the curve from 0 to pi over 2 cosine x dx, which is now going to be the area from starting here and ending here, which is the area of the first two rectangles combined, which gives me 1.02. So now g of 3 pi over 4, which is just short of pi, is going to be the area starting here and ending here, which is going to be the area of my first three rectangles. And as you see, these two are going to cancel each other out, and I'm going to be left with a positive 0.726. G of pi, I'm going to subtract negative 0.26. Okay? If I go the area so far, area from 0 to pi, is going to be the area of the first four rectangles, which is going to give me 0. As we want to do is we want to plot these points, similar to what we've done up at the top when we did the slope and the derivative review. Okay, so if I start at 0 to 0 and I have 0 area, okay, this is my area so far. I'm starting with 0 area. As I move forward, okay, as now I have a grid coordinate, pi over 4, 0.726, this tells me my area so far at that x coordinate. So when x equals pi over 4, I have a value of 0.726. At pi over 2, I have a value of approximately 1. So here's pi over 2, I have an area of approximately 1. Okay, now I'm at 3 pi over 4, and I have area so far as 0.726. Okay, so now instead of writing these down, I'll just plot the points. As I move to my next point, at pi, I have 0 area. 0 area so far. I go another interval, I have negative 0.726. I continue on, I have negative 1 at 3 pi over 2. Then I have negative 0.726. And I finish at 0. And if I have more subintervals, or if I fit a curve to the line, you see the curve that we've created is the sine curve. At the beginning, we said that the derivative was the slope, so if we took the slope of the sine curve at any given point, that slope became plotted values and became the cosine. Therefore, the derivative of sine is cosine. So the antiderivative, or the integral of the cosine function, is the area under the curve, and if I add up the area that I have so far, that'll tell me the value of sine of x, or g of x, which in this case is the sine curve. Another example to illustrate this point is if I graph the function 2t and I find the area under the curve, I should get the integral of 2t with respect to t, which should be 2t squared over 2 plus c, or t squared plus c. This is what I should get. So by adding the area under the curve, in this case, I'll use triangles and trapezoids, which is 1/2, my base is 1, and my height in this case is 2, which gives me an area of 1. Okay, to continue this example, I've calculated the area of the first 4 triangles and then trapezoids as 1, 3, 5, and 7. If I add up the area so far, starting at 0, I have 0 area. The area from 0 to 1 is the first triangle, which was the area of 1. It gives me at x equals 1, I have 1 unit of area. When x equals 2, I have the area so far, the area of the first 2, which gives me first and second, or 1 plus 3 is 4. So when x equals 2, I have 4 units of area. When x equals 3, I have 9 units of area, or the combined area so far of the first 3. The first 4, when x equals 4, I have 16. So as I plot these points, x equals 0, I have 0. X equals 1, I have 1. When x equals 2, I have 4. When x equals 3, I have 9. And when x equals 4, I have 16. And if I fit the curve to that line, it becomes the x squared. For a more simple function, the function is y equals 1, and if I put rectangles under the curve with an interval of 1, so this becomes my delta x. Okay, the area of the first, if I start with 0, the area so far is 0. As I move forward to 1, the area I have from 0 to 1 is 1 times 1. The area I have from 0 to 2 is this additional area of 1 plus 1. It gives me an area of 2. Total area so far. The area so far from 0 to 3 is 3. And if I fit a curve to this line, it's a straight line with a slope of 1, or y equals x. So the integral of 1 with respect to x is x, and the derivative of x is 1.